All right. Well, hello. Thank you. I like that interaction already. So thank you for joining us. We have a very exciting talk coming up. I'm Greg Heston. I teach in the physics department and am the Associate Director of Science Ed. And on behalf of the university Division of Science, the Harvard Bookstore, the Harvard Library, I want to welcome you to this event with Professor Matt Strassler, who will be discussing his book, Waves in an Impossible Sea. Before we get into all of that, I just want to give you a little bit of information about this series. It's the Harvard Science Book Series, Harvard Science Book Talks. If you want to know more information, just Google that, Harvard Science Book Talks. You can learn about future events on YouTube. Search it. You'll find our library of past talks. Great talks to watch. Our upcoming events, some great talks. We have Sean Carroll, May 13th, Quanta and Fields, the biggest ideas in the universe. We have Venki Ramakrishnan talking about why we die. April 17th, we have Leslie Valiant, who's talking about the importance of being educable, a new theory of human uniqueness. So we have some great things coming up, but what we're most excited about right now today is Professor Matt Strassler talking about his book. Professor Matt Strassler is a theoretical physicist, blogger, and writer. His research in particle physics and quantum field theory takes him across the globe to CERN's Large Hadron Collider, all the way in beautiful Switzerland. In recent years, he's been an associate of the Harvard Physics Department here. And he was also a visiting professor in 1997 and 2013 because we just love having him around. He's a former member of the Institute for Advanced Study. He was previously a professor at UPenn, University of Washington, Rutgers. Everybody wants him around. He's also, and this is relevant for the talk, he's also a musician. He says amateur musician. I think he's just being humble. We're going to have to find a piano. I was actually trying to remember when we first communicated, and so I checked my memory, also known as my Gmail. I actually reached out to Matt asking him, I was working at Nova PBS at the time, and I said, will you write a blog post for Nova PBS about the Higgs boson or about supersymmetry? And the reason why is because I'd just been getting out of grad school then, and everyone in grad school knew that there was this blog that you go to if you want to check, okay, that news article about that thing that happened at CERN, these particles colliding, and they had this, was it a discovery? We're not sure. Let's check this blog at professormattstrassler.com called Of Particular Significance. Great physics pun. It really straddles the line between sort of expert knowledge, really correct physics explanations, and something that's approachable for the layman. And you know, just from reading that blog, friends and I, we just came to realize the way that Matt was writing in the blog was he would take his knowledge from being a very experienced researcher in many fields, and he would think about them, he'd break them down, and he wouldn't just take other people's explanations. He would build them back up and repackage them in a way that was approachable, but also it was getting all of the physics right, which is also what he does wonderfully, entertainingly in his book, Waves in an Impossible Sea. I was very excited that we didn't just get a blog from you, we got a whole book that I very much enjoyed. It really, sort of explain everything in a way, unify it in this very nice way that you do. And I'll be excited. We'll talk more, but so we'll have a presentation by Professor Strassler, and then we'll talk a bit, and then there'll be a Q&A. So when we do the Q&A, just wait for the microphone to come to you, and please keep the questions brief if you can. And then after that, we'll have a book signing across the hall in the library, and there'll be nibbles of cheese and juice and nice things like that. And with that, take it away.
Well, thank you Yes, there we go. Thank you for all braving the winds and the impossible rain to come here tonight. I appreciate that. It's a real pleasure to be here and an honor. I've been an attendee at many of these wonderful lectures, and I hope to add to the collection tonight. So I want to start with two questions that at first glance might seem that they're completely unrelated, or they're almost opposite to each other. The first question is, what is stuff? What am I made from? What is the room made from? What is everything around us made from? And the second question is, what if you take all the stuff out? What's left? What is empty space? And part of the point of this book is that these two questions are actually very deeply tied together. And I hope to convince you of that tonight. So we all learned in school that we're made of atoms. Atoms are real things. You can see them in microscopes. This is a microscope picture. Every little ball in there is an atom. But when you want to see what's inside an atom, well, you can't literally see it. That goes beyond what our microscopes can do. And so we do various experiments, and then we start drawing pictures. And everybody's seen the picture, right? Here it is. And this is not a picture of an atom. It's a cartoon of an atom. And like many cartoons, it's not very accurate. So for example, the nucleus is the core of the atom. It consists of protons and neutrons, but it's nowhere near as large as it is drawn. It's really very tiny. I can't even draw it as small as it actually is. If an atom were the size of this room, the nucleus would be the size of a tiny pebble. So atoms are mostly empty, which is worth keeping in mind. And then we have the electrons. Well, the electrons are not little yellow balls. They're elementary particles, and you're going to see me use quotes around particles for most of this talk. They're not really little spheres that you would shrink down to a tiny size, which is, the word particle evokes that in our minds. That's what we think of in English. We think of a tiny object like a dust particle, and we just shrink it down in our minds and think, oh, that must be what an elementary particle is. But it's very important to understand it's really not what electrons are. And maybe the best way to draw them, at least at first glance, is to say, well, they don't really orbit around the nucleus. They kind of surround it. And what kind of things are electrons that they can do that? Well, that question troubled physicists and occupied physicists for many decades. And over time, they came to a conceptual and mathematical language for understanding electrons and other elementary particles. And I want to say a few words about that language, because in some ways, that's the main topic of this book. So this language has its origin in the 19th century. And it comes from when physicists were trying to understand electricity and magnetism and the relationship between them. They developed the notion of the magnetic field. That is the thing which makes your compass point north. And the electric field, that is the thing which causes static electricity, like when you take your a wool hat off in the winter and your hair stands on end, or here you've got a comb pulling a little piece of paper. And then they eventually understood that light itself is an electric and magnetic phenomenon, specifically a wave, which we call an electromagnetic wave. So these things were understood in the 19th century. And then along came Einstein at the beginning of the 20th. And Einstein added two key ideas. The first was that he revised the notion of the relativity of motion, of space, of time. And in the same year, this 26-year-old fellow introduced the idea of the quantum. Now, quantum physics has a little bit of a prehistory before Einstein, a few years. But Einstein is the one who got it right in terms of what it meant to be quantum. And the language of particle physics today is known as quantum field theory. The field part comes from the 19th century. The quantum part comes from Einstein and those things that followed from him. And then there's the word theory, and I have to say a few words about theory because there are so many words we use in science that have meanings that are different from the ones that we have in English, and this constantly causes confusion. This is a sub-theme in the book, in fact. So the word theory here in English tends to mean a speculation. It's sort of the opposite to the word fact. But what we mean in science is something quite different. This is a combination of concepts and math. There's some mathematical equations and some concepts that tell us how to use them, how to employ them to make predictions for experiments. So the word theory here should not suggest to you that we don't understand how this works or that we're not sure that it works. It makes wonderful predictions for experiments. In fact, there's not a single experiment anywhere which is known to violate this language of quantum field theory, which is a remarkable achievement. Now, quantum field theory had its origin in the 1950s, but it really only took root deeply in the 1970s with the rise of modern particle physics and our understanding of it. And over the 50 years since then, it's gradually taken very deep root and is so well established now that it's really a good time to take a step back and ask, okay, this is the language for now and probably for some time that we use to describe the world. What does it teach us about the universe itself and about us and about how we fit together with the universe? So I want to come back to my first questions. Now, I already addressed a little bit the question of what we're made of. So let's look at the second question. What is empty space? And what do I mean by empty space? Well, I literally mean let's take a box and let's take everything out of it. Okay, remove all the stars and all the dust and all the atoms and the light and the neutrinos and everything you can think of, everything that can be removed, take it out of the box. What remains, by definition, is empty space. But what is that? Well, in Newton's day, we thought of it as just this big emptiness. And that's, in fact, how most of us think about it, right? You go out at night, and this is gigantic emptiness, this empty space that the Earth floats around in, and I guess there's stray atoms floating around, and maybe there's an astronaut floating around in there. It's just emptiness. And these lonely little things move around within it. But then Einstein came along, and Einstein said, well, all that gravity that holds the planets around the sun and holds us to the Earth, it's actually a manifestation of space being curved. Oh, and you may have heard that the universe is expanding. That does not mean that the stuff is expanding. It literally means that the space out of which the universe is made is growing. There is more space in the universe now than there was a billion years ago. Gravitational waves, you may have heard of them. They won a Nobel Prize in 2017. They're ripples in space. So how is it that space can do all of these things? Well, let me take the opportunity to read a paragraph or two from the early part of the book. We used to think of space as a benign, boring nothingness. But after Einstein suggested that gravity reflects the bending of space and time, we learned that empty space itself can warp, stretch, and ripple. It's hard to imagine that nothingness could do these things, which seem more characteristic of materials, such as fabric or rubber. Yet if space behaves like rubber, why can we move through it as though it's not there? So in other words, air is a material, and if you want to move through it fast, like a plane, well, a plane needs to move fast to remain flying, but it needs engines. It needs to be running its engines all the time, or it will slow down and fall out of the sky. But the Earth is moving through space right now without an engine. It's been doing it for billions of years. It's not slowing down. In other words, air creates resistance if you try to move through it. Space doesn't. Now, why is that? How is it that a plane has trouble going through air, and we have no trouble going through space? Well, here's a clue. There's something in this room which is going through air without resistance at hundreds of miles an hour, and you can hear it. Sound waves go right through the room without slowing down. They can go long distances. So Could it be that space is kind of a material that can warp, ripple, and stretch, and that we move through it because we are waves in some way, made of waves of some type, or in some way incorporated into space? In other words, maybe the picture we should have, rather than this one, where we have these lonely things floating in blank emptiness, should be more like this, where space is actually kind of like a material, and elementary particles are waves of that material, and our astronaut and our planet are made from those waves. And so rather than this picture, we have this one. So think about that for a minute, how different these pictures are. Now, I don't want to claim that this picture is definitely known to be correct. But what I will tell you is that this picture is very far from what quantum field theory says. The mathematics of quantum field theory tends us towards this picture. And Einstein's notion of space also tends us towards that picture. Not entirely established, but I think it's a good picture to be working with because it makes the workings of the world clearer in a lot of different ways. So let me read again a short passage. So what does it mean that we move through empty space, through the universe, without space resistance? Our drawings and our depictions of basic physics subtly lead us to imagine ourselves as made from ingredients that exist within the universe. But perhaps that's not so. It seems as though we are made from waves of the universe. I do not mean this in a spiritual or metaphorical sense, though there's no harm in those resonances if you are inclined to hear them. My meaning here is concrete, tangible, real in the scientific sense. I'm suggesting that our very substance is the cosmos in action. So, to see that another way, rather than thinking of these objects in empty space as sort of floating around and drifting through an emptiness, we should perhaps instead think about waves of a substance moving through the substance, somewhat as sound waves move through air. Now, I need to take one more moment to address another word in the English language which causes problems. Because I've been saying we're made of waves, better check the word wave. Okay, so if I give you a picture like this, which shows a wave-like phenomenon in a substance, many of you will surely think, that's one wave here, that's another wave here, and that's another wave here. That's the way we talk about waves at the beach. But this is not the way scientists talk about waves, at least not in this context. So if we have a wiggly wave like this one up at the top, we tend to say that's a wave in ordinary English. But what in fact we mean in science is that this whole thing, this wave set, is a wave. And when I say we're made from waves, I'm not saying we're made from individual wave crests, but we're made from these structures that have many crests and troughs in general. And one of the reasons that's important to make clear is because when a wave goes by you, there is a notion of the wave's frequency. How often does a wave crest pass a particular point? Okay, here comes a wave crest, here comes another wave crest, here comes another wave crest. That sets a frequency. And frequency will play a role in what I have to say in a minute. Okay, so let's look at how far we've gotten. So look at where we are so far with our questions. Well, we're made of elementary particles. Those include electrons. They also include these things called quarks, which are what neutrons and protons are made from. And then empty space, maybe it's a sort of somethingness, and maybe we're made from some sort of waves in that somethingness. But there's just one problem. It's a nice picture, but that somethingness that might be space has to have some very strange properties. So strange that it's impossible for any ordinary substance to have them. Let me explain what I mean. I'll explain one of them. It's not the only one. Okay, so let's take the floor. The floor is made from concrete. It's a perfectly good substance. You are stationary with respect to the floor. I am currently moving relative to you. Therefore, I am moving relative to the floor. Pretty obvious. And true. But now let's come to space. Let's say you're stationary with respect to space, and I am moving relative to you. You may be surprised to learn that I am also stationary with respect to space. You're stationary, I'm stationary. That is a very strange thing, and no ordinary property, no ordinary substance could have that property. In fact, that property is only possible because of the strange ways that space and time work that Einstein uncovered at the turn of the last century. Now, let me be a little clearer about what I mean. What I mean is, if you attempted to figure out how fast you're moving relative to space by doing any measurement you could think of, you will fail. You will never see any sign that you're moving with respect to space. Nor, even though I'm moving relative to you, will I. And this is not true of air. It's not true of water. You can always tell if you're moving. There are lots of ways to tell. But with space, you can't. So if space is a substance, it's a very strange one. And maybe this whole picture of it as a substance isn't right. It's useful. It gives us a way of thinking that's different from space as emptiness. But still, we have to be a little cautious about it. All right, let's now see another aspect of this. So elementary particles, they're waves. But here's an interesting feature. For some of them, they have not just frequency. They're waves, so they have frequency. But they have preferred frequencies. There's special frequencies. Electrons have a special frequency. Up quarks have special frequencies. Individual types of neutrinos. What this frequency? That's a very interesting thing, because what that means is, if you think about the universe as a whole, it's an object that has waves in it and preferred frequencies. What do you know from daily life that has those properties? Well, those of you who play musical instruments know that musical instruments have waves on them, and they have preferred frequencies. Those are the notes that the particular instrument makes. And there's a reason for this similarity, and that is the central role in both cases of resonance. So let me, again, quote briefly from the book. Resonance is the foundation for most instruments that can make a steady, sustained tone. Bells, guitars, violins, pianos, pipe organs, flutes, trumpets, xylophones, and many more. It's resonance that makes playing the instrument predictable and its notes reliable and steady. Without resonance, making music would be dramatically more difficult. Making humans would be dramatically more difficult, too. In a very real sense, resonance underlies the entire cosmos, dictating properties of the elementary particles out of which we and everything else are formed. It is here that we find parallels between our universe and a musical instrument. Now, this all sounds very beautiful, poetic, maybe even kind of mystical. And some of you are surely wondering, what the heck is this guy talking about? Made from waves? What have you ever seen in your life that is made from familiar waves? I mean, if you want to build something, you want bricks or stones or steel. You want something that you can stack and organize, something that when you put it there, it stays there and it's going to last. Okay. I don't know any contractors who work with waves, with water waves, with sound waves. I mean, who builds boats out of water waves? I mean, come on. That is not good building material. Waves tend to slosh, they tend to spread out, they don't stay where you put them. This is a really bad way to build things. Okay? Now, clearly we're missing something. And there is indeed something about the universe's waves which is different, at least it's different from the concepts that we have for ordinary waves that we encounter. We don't realize that this is possible. And it is a very strange property, which nobody guessed until Einstein. So waves in the cosmos have this special feature. They're kind of made from ingredients. So let me give you a couple of examples of other things that are made from ingredients. that you'll recognize? Well, the simplest would be a pile of sand. I mean, if you come across a pile of sand, if you didn't know better, you might at first think it's sort of a continuous substance. But then, of course, after a little investigation, you discover it's made of grains. Now, these really are particles now, particles without the quotes. Right? These are particles of sand, little tiny things, and you put them together and you get a sand pile. But they're not the only thing. Like this, suppose you take a rope and you untwist it as far as you can. Eventually, you will discover that your rope is made from strands. Now, you might call those particles of rope. You probably wouldn't, but you could. They're the sort of minimal bit of rope out of which you construct the whole rope. Right? And in a similar way, you might take a stack of paper, which would look like a single block from a distance, but of course it's made of individual sheets, particles of paper. And the point here is that there's something similar to be said about light. So let's take a flash from a laser beam like this one. Okay, what does it look like? Well, it's some kind of wave, some kind of electromagnetic wave. The details don't concern us, but it is a bright light. So these are big waves, big wave crests, big wave troughs, the sequence of them with a nice frequency. What are light waves made of? Well, they are made of particles of light, but there's a better name for them. At least there's a name which was invented in the 1920s and kind of got lost for a while, but it's making a comeback, so I'll use it here. Light waves are made of wavicles. And what are wavicles? Well, they're the minimal ingredient you need to make waves. So they sort of look like this. Okay, so here's our big wave, and here's the little waves out of which they're formed. This picture isn't exactly right because we're doing quantum physics here, and quantum physics can never be properly drawn. But this is a pretty good image for giving you the idea that there is a minimal type of wave out of which the bigger waves are made. And we'll call them wavicles, and in the case of light, we call them photons. Now, there's a key difference between the particles of sand, the threads of the rope, and the sheets of paper compared to photons, which is that a grain of sand, we can, in fact, cut it in half. We could slice, we could cut a thread of a rope, and we could rip apart a sheet of paper. But photons are truly elements of the universe. They are indivisible. Nothing you can do can ever make half a photon. So now our waves are made of ingredients which are indivisible. Sounds like we've got our bricks to make things. Not quite, doesn't quite work. Because, well, light moves at, always, the speed of light. And photons are just little bits of light, so they too move at the speed of light. Not very convenient for building things. Okay, so that will not do. Photons never stop moving. But electrons are wavicles too. And electrons can slow down and stop. And so they can be both waves and bricks. And that is the key secret of quantum field theory. That is how the cosmos works and how quantum physics makes it possible for waves to be building blocks. It's this feature that electrons and other fundamental particles are really wavicles. They're little waves that can slow and stop. And so these elementary wavicles, electrons and the quarks that make up protons and neutrons, they can be put together. They can make atoms. The atoms can be put together to make molecules, which can then be put together to make larger things, including humans and buildings and planets. And they have this nice property. They'll stick around. They'll stay where you put them. They'll even stick around in the case of the Earth for billions of years. And indeed, all of the things around us are made from these types of wavicles. Now, the reason, there's a key reason that these wavicles have this property, that they can slow down, stop. And that is that they have a property called mass. And I'll spend a couple of minutes now on that. Mass is very important. You would regret it if you didn't have any. On an evening like tonight, you're doing better than your hat or your umbrella, because your hat's mass compared to its size is small enough that the wind can blow it away. Whereas you and I have enough mass that relative to our size, that the wind doesn't affect us. We can use our mass as armor to fight off the slings and arrows of nature. If we were unlucky enough to suddenly lose 90% of our mass and we went outside after this lecture, we would have a different experience. So mass is really critical for survival. Okay, you can't survive in the world without it. This picture, by the way, appears in the book. It is one of a number of illustrations, about 40 to 50 of them, many of which were done by a physicist, a young physicist who is in the audience, and an MIT postdoc, former Harvard physics PhD. She works on things like the muon collider, and you can ask me or her about that later. But anyway, so she's a very fine physicist, and like many fine physicists, she's multi-talented, and this is what she does in her spare time. So you can enjoy her other pictures in the book. But let's come back now to mass. You have some, I have some, it's all very important. Where does it lie? Well, of course, we're made from atoms, so the mass is in the atoms, but where is it? Well, the vast majority of your mass sits inside your atomic nuclei. And there's an interesting story about where that mass comes from. It involves the strong nuclear force and the Big Bang. That story is in the book, but I'm not going to talk about it here. I want instead to focus on the less than 1/10 of 1% of your mass, which sits in those electrons. It's such a tiny fraction. I mean, of my 150 pounds, it's much less than a 1/10 of a pound. It seems pretty irrelevant, but it's not. Now, that little bit of mass comes from a different place. It comes from something called the Higgs field. I won't have time to really go into it here. It's discussed in great detail in the book. But it's an idea which came about in the 1960s, and yet wasn't confirmed until just a few years ago with discoveries made at the Large Hadron Collider. Now, this Higgs field is extraordinarily important. It is one of the top 10 ingredients for life. And you might wonder, why is that? I mean, all it's doing is contributing this tiny little bit of mass. Well, there's a critical reason. If there were no Higgs field, then electrons wouldn't have any mass. And what would happen then? Well, if you were to take electrons around the universe and you were to cut their mass in half, atoms would double in size. And if you kept doing that, if you took the electron's mass all the way down to 0, the electrons would just wander off the atoms and be gone. There would be no atoms at all. So the Higgs field is an essential part of life because without it, there'd be no atoms, and we wouldn't exist. Well, there's a natural question that you might ask. I've told you that somehow electrons get their mass from this Higgs field thing. How does that work? Well, there isn't really time to explain that. In fact, there wouldn't have been time to explain it in 30 minutes. That's why I wrote the book. It's a little complicated, but it's not too complicated. It's something which an average person can understand, but it takes just a few steps. So if you want to understand how does the Higgs field produce an electron's mass, you first need to know that particles, in quotes, are actually wavicles. That's a key step. And then you also have to know what the mass of a wavicle really consists of. And you have to learn why there's a relationship between wavicles' masses and their frequencies. And you have to be able to understand a question like this one. Why do all electrons, all across the universe, every single one of them, have exactly the same mass? So all of these questions are answered in the book, but they take a while. Now, there are some other questions that are answered in the book, sort of not along this track, but they're related. For example, a proton is not a wavicle. A proton is made from many wavicles. Where does its mass come from? Why do all protons have the same rest mass, same mass? How do protons get made? Well, it turns out that quantum fields and the Big Bang have a big role to play in that. And here's another question, not obviously related, but it sort of is. I told you earlier that atoms are mostly empty. That means I'm mostly empty. The floor is mostly empty. Why am I not falling through the floor? Why are you not falling through your chair? Why do tables seem solid? Well, the answers to these questions, all of them, come from quantum field theory. Every single one is answered by quantum field theory, and all of them are addressed in the book. So the answers are there for the reading. All right, so let's pull it all together. All right, so we're made of elementary wavicles, electrons and quarks and the like. These are some sort of minimal indivisible waves. They're waves in a somethingness, which is empty space itself. Empty space is not so empty. It has processes and things that happen in it. And those waves wouldn't be useful for making stuff if they didn't have mass, so that's why the Higgs field is very important. And yet that story, always we need to remember, it's a really nice story and it almost works, but there are those impossible properties that space has, which have to make you wonder, certainly make physicists wonder, is this the right picture? Is there somehow a twist in it that we're not getting? Or is it somehow misleading and it's completely wrong? There's something totally different going on. And we don't know. That's current research. So I hope this book will give you new ways of thinking about the universe that you and I live in. And in particular, that it will give you ways, a different way of seeing how we fit into that universe, how we are a part of it, incorporated into it, a manifestation of it. And I hope also that in doing so, I have succeeded in drawing the line and drawing distinctions between what we really do understand and what we don't. There's a lot we don't understand. And even about the things we know, there are these nagging questions that sit beneath them all. So let me conclude with one last quote from the book. Of these links between the human world and the universe, what was known when Einstein was born in 1879? Essentially, nothing. The empire of Newtonian physics was eroding, but it had not yet been toppled. The concept of a field had been developed, but subatomic particles hadn't yet been discovered, much less any relation between particles and fields. Many scientists believed in the existence of atoms, but there was as yet no direct evidence. Unsuspected were the cosmic limit on speed and the uncertainty principle. No one imagined wavicles, much less a relation between gravity and curved space, or that the universe might be like a musical instrument. The basic underpinnings of ordinary matter and of the human body in particular were completely mysterious. And yet, no one guessed how truly mysterious they would turn out to be. Thank you.
Okay, well, I feel honored that I get some of the first questions before all of you get to ask questions. Thank you, that was wonderful. You started out the book and you sort of described that part of your motivation, at least in the beginning for writing the book, was that the way that, at least in public media, people had been describing the Higgs boson, the Higgs field, especially when it was discovered around 2012, and I think still now, wasn't sufficient, or there was something that you wanted to explain more about the Higgs. Why did you think that it wasn't sufficient, and why was it so important that it made you think, like, I need to write a book?
Well, there are always compromises that scientists have to make when trying to explain what they do in a short time and to people who don't want to be experts. Compromise is always necessary. It's even necessary when you're teaching. You choose to teach certain things and leave other things for a later course. But ideally, the compromises you make should not be deeply misleading and profoundly false. And unfortunately, the compromise that was made broadly when it came to the Higgs field to try to explain how does it give mass to things like electrons had multiple serious problems. And I'll give you just a sense of one of them. So the idea was, well, the Higgs field is like a molasses or a soup. and it fills the universe, and as things try to go through it, it impedes them, it slows them down, and that's what gives them mass. Now, we were just talking earlier about the fact that the Earth has been going around the sun for a long time. The Earth has mass. It is not slowing down. So how can its mass come from something slowing it down? Right? It doesn't make any sense. And it doesn't. I mean, the explanation is wrong. It violates Newton's first law of motion and Galileo's principle of relativity as well as Einstein's. So in my view, if you're going to make a compromise, let's try not to violate the first thing we teach first-year college students about how the world works. Because at best, you're going to confuse them, and certainly you're not explaining anything to them. You're just making a mess of the situation. And in fact, the real way that the Higgs field works has nothing to do with motion at all. It has to do with that thing I mentioned about masses and frequencies of wavicles. So you have to learn a bit more than most people know about the universe in order for it to be easy to explain. In the end, it's not that hard, but a lot of the things that go into it are things that are not widely known. And so I wrote the book in part so that many of those things would be easier for the average reader to learn and to grasp, and then the Higgs field could be explained correctly. So ideally, if 50 million people read my book, then we can dispense with the old explanations and go with the new ones. So help me out there.
That's great. So you redefined a few words for us.
I did.
Theory, wave. Just in case we're out in the world reading some other books or reading some articles, are there other words we should watch out for?
Oh, I guess there's 7 or 8 mentioned in the book. I mean, one of the worst is the word mass that I myself had to use at the end of this talk. I'll warn you that there are conflicting statements about mass that you may already have run across. And in the book, I'm very careful. Here, I didn't have time to be careful. But in the book, I'm very careful to delineate them. For example, many of you will have read that mass increases with speed. And you will also have noted that I said that every electron in the universe has exactly the same mass. But of course, they don't all have the same speed. So how can these two statements be true? It's absurd. And the answer is, well, since Einstein, there are different notions of mass floating around. And unfortunately, in many articles by scientists and by journalists, they don't tell you which one they're talking about. So this leads to endless confusion. So that's a really good example because it's a fundamental word, and yet there's multiple notions of it, and most people are unaware of this. So that's one. Another word that's really a problem is matter. Physicists use at least 2 different definitions of matter, and astronomers use 2 other ones. So even within the scientific field, there's potential for confusion, and students do indeed sometimes get confused. Everyone agrees that atoms are matter and that light is not matter. But then when it comes to all the other types of particles, well, it depends on context, depends what people mean. Dark matter, for example, by some definitions, may not be matter at all. So these are the types of words that cause a lot of confusion for readers and spectators of science. And I would hope that we as scientists could start to do a better job and a cleaner job of defining what we mean so as to gradually reduce those confusions. Though, of course, there are a lot of books out there that already exist, and this won't be a quick process.
So the book, so you start off and you redefine all of these things. You give us a new way to look at many of the things that in a physics class students might even learn in the original way. So it's very nice that you redefine it, and then you get around to the Higgs and very advanced topics. And then in the end, you describe some of the big open questions. And so since we didn't quite get to some of those open questions, I was wondering if there are any of those that are striking or that stand out to you as exciting, something that, maybe where are we with physics right now?
Well, I can't speak to physics as a whole, of course, but as far as particle physics and quantum field theory and so forth, I think one question is sort of implicit in my slides about space. One question is, does space really exist? It's so weird. Or if it exists, What is its origin? How can it have these strange properties? This is an area of active research today among theoretical physicists. We don't, unfortunately, have any near-term hope of doing experiments on that question. Meanwhile, though, the discovery of the particle known as the Higgs boson, which is a wavicle of the Higgs field being the really important thing, the discovery occurred back in 2012, and there's something rather odd about the set of particles we know, including the set of particles and fields that we know, which is that anytime we try to write down a consistent and complete theory, we don't have a complete theory of all of the particles of nature at this point, but if we try to write one down, one that would predict some of the properties of the Higgs boson and the Higgs field, we always find that the theory contains additional particles and fields that should have been discoverable at the Large Hadron Collider, the world's largest accelerator where the Higgs boson was discovered. And we've been running for 10 to 12 years since the discovery of the Higgs boson, studying the Higgs boson in great detail in order to learn more about the Higgs field. But along the way, we haven't found anything else in the form of an elementary particle of some type. And that seems to contradict our understanding of how the Higgs field ought to work. So this also makes us a little worried, because when we came in to the era of the LHC, we did have this, we had these examples, all of which suggested the Large Hadron Collider should find additional particles. And the fact that it hasn't now poses a puzzle. Are we thinking about the Higgs field wrong? Are we thinking about quantum field theory wrong? Are there particles at the Large Hadron Collider that are hiding from us? That happens to be, the last part is a lot of my own research. It's true that the Large Hadron Collider has vast data sets, and when you have a gigantic amount of data, if you don't ask exactly the right question, you might not see what's actually in there. So we have to be very thoughtful about all the different questions we should ask of this data. And so I think one of the areas that we really have to focus on as theorists and as experimentalists is this puzzle, which not everyone agrees is a serious puzzle, but most people in the field do. And the problem with having a puzzle like that is that when you have a rough idea of what you think is going to happen, you know which experiment you need to do in order to find out. And when you come to a point that you no longer are sure which direction you should go, that also makes it harder to figure out what the relevant experiments are. And so one of the challenges we face in the field of particle physics today is that there are a lot of different directions we could go, and there might even be directions we should go that we haven't thought of. And so it's not as clear as it was, let's say, 50 or 30 or 20 years ago, where we should go next. So that's an important aspect of the field right now.
That's exciting.
I think so.
Just to prepare for everyone's questions, maybe you could tell everyone what your research is, like what are the fields that you do work on, just broadly so that people can get a sense.
Well, over the years, I've worked on a lot of different things. I've worked on string theory, I've worked on quantum field theory, and I've worked on particle physics. But these days, as I'm becoming a senior member of the field, I have to choose carefully. And for me, the mystery that I just mentioned about the Large Hadron Collider's lack of additional discoveries at this point, the fact that it confirms that our story of quantum field theory and the Higgs field seems to work better than we might expect, that for me is a key question, because this issue of where the field should go next depends critically on the question of whether there are new particles in the Large Hadron Collider's data or not. And therefore, it's critically important that we do a thorough search of these huge data sets. And to do a thorough search requires creativity and thoughtfulness about all of the different ways that new physics might manifest itself. So if we don't think of all the different curveballs that nature might throw at us, we might not see them. And so my job, as I see it, is to devote my attention to the existing collider and to make sure we get every ounce of data out of it, every ounce of information out of it that we possibly can.
All right. Well, if you have a question, just go ahead and raise your hand, and either Cassie or I will come to you.
I was wondering if you thought about dark matter and how you might observe dark matter at the LHC in some manner. And I heard also they're trying to build a longer one to accelerate particles faster.
Let me address the dark matter one. If I have time later, I'll come back to the issue of the future collider. Dark matter, what we know is that galaxies don't rotate the way we would expect based on the matter we see. There are other things that happen in the universe that don't seem to reflect the matter that we see, and therefore we infer that maybe there is something else out there that's subject to gravity. And we call it dark matter because we don't know what else to call it. There are people who dispute whether it exists. They are a minority, but they are vocal, so we should not forget that it's not 100% certain that it exists. But if it exists, the problem is we don't know what it is. We don't know if it's particles of very low mass, if it's black holes, or anything in between. And we don't know if it interacts with ordinary matter in a relatively strong way that we could discover today, or whether its interactions with ordinary matter are very, very weak, and it might take 1,500 years before we have the technology to find it. So the problem with dark matter is that it is a vast range of possibilities. And there is no way to know if we are on the verge of discovering it or if it lies many decades or centuries away. We can hope that as we learn more things about the universe, we will get more information about that. We can also hope that we'll stumble on it. And certainly the LHC could stumble on it, although to be more precise, the LHC would have a heck of a time, even if it made dark matter, it would have a heck of a time figuring out that it was making dark matter. All it would know is it's making some object that's really hard to detect. You would see such a thing by, how can you see something you can't see, right? Well, if you make a little explosion and some sort of particle collision, and things you can't see go this way, well, then things you can see go this way, and you see the event is unbalanced. But that's all you know. You can't, from that alone, deduce that that's the dark matter of the universe. So it is a long way from LHC discoveries and other sorts of studies to convince yourself that, LHC, the Large Hadron Collider, has really made dark matter. And one of the ways you might do that is if dark matter comes along with friends, which are not so dark and can be observed, maybe if you're very lucky, you can work out the properties of all those particles and infer that the particles you're making might be dark matter. But you still can't really show it by the LHC alone. So the dark matter search is a long-term, multi-experiment search, and we have no idea how long it will take.
Good evening. I'm wondering about the tools that you use to analyze the data from the Hadron Collider. And do you have the tools you need, or is that an area of research that is ongoing? And has AI got anything to do with that?
Particle physicists have been using artificial intelligence of one sort or another for many years. It depends on what level of artificial intelligence you mean. For example, neural networks and boosted decision trees have been part of particle physics now for basically since the LHC began. We'll use whatever tools are available as long as we can figure out how to make them useful. Now, the reason you can't just throw artificial intelligence at a problem like this is that the Large Hadron Collider is an extraordinarily complicated experimental environment. First of all, you've got these proton-proton collisions, and each one makes a splat. So you've got a lot of stuff. There's something happening inside that you're interested in, but then there's a lot of other noise coming out that you have to pay attention to. The machine, the way it works is you fill up the beams, and now you have really strong beams. You have lots of collisions, and gradually over time, the beams become depleted. So the rate of collisions is changing. Your detector has got high voltage and all sorts of fancy things. It's constantly drifting around. You have to keep track of that. And so you need a real team of people and a lot of bits of data to put all that together and to make sure that a sort of overarching artificial intelligence could do that correctly. Well, it would be very challenging, but it's not obviously impossible. The other thing you need to know, though, is that you need to understand all of the things that you expect to see before you can say, I'm seeing something unexpected. And that, too, involves an enormously subtle, complicated problem. Because while it is true that quantum field theory predicts, in principle, everything that will happen at these machines, in practice, some of these calculations are very hard. And that's not something AI can help you with. It's mathematical technology or even computer power. So to really predict what should be there at the level that you can detect something that, quote, shouldn't have been there, requires, at this point, a great deal of human intelligence. And I don't think AI is there yet. So I would say it this way. Experimentalists are certainly fully aware of the potential of this technology, but it's going to be a tool which they use. It's certainly not going to replace the experimenters anytime soon.
Hi, Matt. Thanks for a great talk. So I wondered if theoretical physicists are still hoping to find unification, the idea that all of the different fields and forces are different facets of the same thing, whether that's sort of what you're hoping to get with the next set of experiments?
Well, you asked this question with Howard Georgi in the audience. Howard and Shelley Glashow were the ones who essentially invented the idea of what is known as grand unification. Grand unification is the idea that the three non-gravitational forces that we know about so far, although I should add there's a fourth one, but we can get back to that in a minute. The electromagnetic force, the weak nuclear force, and the strong nuclear force actually are all manifestations of one force, that somehow at very short distances they're the same, and then there are these weird properties of space that make them look more different than they are. And that idea is still out there. In string theory, it becomes somewhat modified, but the idea that all the forces that we know might unify, and perhaps even unify with gravity into a single, simpler concept, that is certainly out there. Now, we don't, at the moment, have any new clues about this. So I don't think there's anything I can say now about it that would have been particularly different from what one might have said 20 years ago, except that people might have said 20 years ago that, well, when the Large Hadron Collider turns on, maybe they're going to discover certain particles which make it more obvious that this unification might be occurring. Well, that hasn't happened. That doesn't prove that unification of forces won't happen. But the way I would say it more generally is this. I gave you this picture of space as an entity. And the fields of the universe that I've mentioned, they're somehow integrated into that entity, or there may be even properties of that entity. So there may be a sort of unified picture of the universe where all of the different fields are in some sense part of a single structure. And the unification of forces may be part of something more general than that. This, however, is all speculation. We don't have any new evidence for it. It's just something that we find is a common feature in theoretical investigations. And we'll have to see. I don't think this is, unfortunately, a question for my lifetime, but perhaps for the youngest people in the audiences, perhaps it will be.
So how do you feel the conceptual gap between the particles, elementary particles, and strings from string theory, which there's orders of magnitude in size difference between them, and the strings are supposed to give rise to the particle with weight, with mass, and so on. And this is just a pure guess. Along the way, is there something analogous to Higgs particle, or what you can call Higgs string, that regulates the strings that somehow give them weight?
So I deliberately did not talk about string theory very much in the book, and there are a number of reasons for that. String theory, of course, is a speculative theory. We have no evidence for or against it. I wanted to make sure the book focused on things that we know or are in the process of learning today. One of the problems is that there are a lot of different ways to answer your question. That is to say, there are multiple ways that there could be, at the foundation of particle physics, notions of strings. Now, one of the things that I would have to explain, if I would explain it properly, is how it is that I can say, well, particles are really wavicles. And now, how does that relate to what strings are? And that is a longer, challenging discussion, and I can't do it properly here, unfortunately. It is true that particles are to strings, and then I have to say that, well, particles are to wavicles, and now clearly there's something else. Right? If I go from particles to strings this way, I go from particles to wavicles that way, I need something in this corner. And that something is hard to describe. It's some sort of string wavicle. Not for today. But in terms of where string theory might or might not fit in, I mean, from my perspective, we don't know. We don't know. It is indeed possible that it is the theory of gravity and all the fields and the theory of space and time. But it's also possible it isn't. And there's always the risk that we humans are, when we discover a candidate, and it's our first good candidate, we have a tendency to assume it must be the only candidate. And we should be cautious about that, even though it might be.
I think that the rest of our questions might have to be asked nibbling some cheese in the library as you get your book signed by Professor Strassler. So with that, give him a hand.